Hello, it's Dr. Daystorms, and the discussion right now is going to be over redox reactions. In particular, we're going to discuss what it means to be for oxidation or reduction, and how to balance simple redox equations. Next semester, when you discuss electricity and electrochemical reactions, you'll go into more complicated redox reactions. But first off, you may be saying, what's the difference between redox and oxidation reduction? And there's nothing. There is no difference. Because redox is just the abbreviated form of saying oxidation reduction. This is actually quite simple. What you're going to find out is that the properties of an atom or an ion really has to do with its electrons. And electrons can move from one place to another place. Now, they don't just float out in outer space and just catch an electron here or there. But it's going to go from one atom or ion to another atom or ion or molecule to molecule. And any time that an atom or an ion loses an electron, it's called oxidation. Any time that an atom or an ion gains an electron, it's called reduction. Okay? And so I've heard a couple of mnemonic devices that can be used to help people remember whether it's oxidation or reduction. One that I heard back whenever I was in college was called Leo the Lion Goes Grr, which stood for losing electrons is oxidation, whereas gaining electrons is reduction. That's one possibility. Leo the Lion Goes Grr. Another one that I've heard people use is called oil rig. Perhaps you can already see where this is going, but oxidation is losing electrons, whereas reduction is gaining electrons. Whatever helps you remember, you should use it. Perhaps you've already noticed, but you can't have one without the other. Okay? Anytime a substance is being oxidized, that means another substance is being reduced. Just like I said, you can't just have an electron go off by itself. Okay? So something is always being oxidized whenever something else is being reduced. The way that we can determine whether something is being oxidized or reduced is using what's called an oxidation number. And I really I don't want to say hate using that term, because I like to think of it as electron bookkeeping. Please do not get oxidation numbers confused with formal charges. Remember, that's what an ion has. That's a formal charge on that ion, if it's a -1 or a +1. An oxidation number is not a charge necessarily. Sometimes they're the same, sometimes they're not. You can have a neutral compound, neutral molecule, and have individual atoms within that the individual atoms within it will have oxidation numbers. It is just a way to keep track of where the electrons are. Okay, it is not formal charge, it is just a form of bookkeeping. Okay, so actually let's go back real quick. So all it is we assign this oxidation number to each element in a molecule or a compound in order to see whether or not it has been oxidized or reduced in a chemical reaction. So how do we assign these oxidation numbers? First off, any element in its elemental form is assigned the oxidation number of 0. So here are some examples that we see. We see carbon, which would be like graphite. Elemental carbon is 0. Hydrogen, which remember, hydrogen is diatomic. It's 0. So for example, also diatomic chlorine would be 0. Diatomic nitrogen would be 0. Sulfur, which you can actually have S8. That would also be 0. All of these are 0. Likewise, one moment, please. Likewise, if you have a monatomic ion, the number is equal to its charge. Now, that's a really fancy schmancy way of saying, you know that the Cl minus anion, the chloride anion, it's going to have an oxidation number of -1. So this is a time when the formal charge and the oxidation number are the same. Likewise, the magnesium 2+ ion would have a +1 charge. A bromide anion is going to have a -1 oxidation number. Sodium cation is going to have an oxidation number of +1. So what happens though in other examples? Nonmetals have negative oxidation numbers unless, these exceptions are oxygen. Oxygen will always be -2 oxidation number unless it's part of peroxide. So what is peroxide? Peroxide is when you have two oxygens that are bound to each other. And whenever that happens, then they're going to be -1. Okay? Usually when we have oxygen, say for example here, where we have a carbon double bonded to an oxygen, this oxygen will have an oxidation number of -2. That is not its charge. It is neutrally charged, but it has an oxidation number of -2. However, hydrogen peroxide, which looks like this, the oxygens will have an oxidation number of -1. Once again, they are still neutral. Hydrogen is interesting. Almost always in this class, you will see hydrogen bonded to a non-metal, and so it will be a +1 oxidation number. However, there are times, especially next year when you look at organic chemistry, you'll see times whenever hydrogen may be bonded to a metal, and then it would have an oxidation number of -1. Fluorine is always -1. All the halogens, like chloride, bromide, chlorine and bromine, and so on, they are going to be -1 unless they are bound to an oxygen ion. So for example, if you have some type of bond that looks like this, a chlorine bound to an oxygen, this chlorine may have an oxidation number of something other than -1. In fact, it will have a positive oxidation number. So like in perchlorate and chlorate anions. Overall, a neutral compound will equal 0. So what does that mean in this example here? So this is ethane, by the way. So let's find out the oxidation number of the carbon in ethane. So we have 2 carbons, and we have 6 hydrogens. The entire compound is equal to 0. And I'm going to do 0 like that, so that way you don't confuse it with oxygen, with the symbol for oxygen. Well, we've already stated that hydrogen has an oxidation number of +1. So this is simple algebra. 2C plus 6 times a +1 is equal to 0. So therefore, 2C is going to be equal to -6. 6. You divide each side by 2, and we have the carbon has an oxidation number of -3. An ion is going to be equal to the charge on that ion. So let's do this as an example. So NH4 plus, the overall oxidation state on it has to be +1. So we have a nitrogen plus 4 hydrogens has to equal +1. Once again, we've already stated that the hydrogen is a +1, so we have nitrogen plus 4 times +1, is equal to 1. So that's nitrogen plus 4 is equal to 1. You subtract 4 from each side, you have nitrogen is equal to -3. Let's do another example. In this example, let's look at sodium sulfate. So this is sodium sulfate, which we've done this before. Okay? And in particular, we need to let's find the oxidation number for the sulfur. So what is the oxidation number on sulfur? Well, the entire compound is neutral here. So this has to have an oxidation number of 0. Sodium is a cation, and remember, each charge on the sodium is a +1. So therefore, each sodium is going to have an oxidation number of a +1. The oxygen is a -2 oxidation number. So let's just do this algebraically. We have 2 sodiums plus a sulfur plus 4 oxygens. This time I'm just going to call it OX, so that way you don't think it's a 0, is equal to 0. Now let's plug and chug our numbers in. 2 times a +1 plus the sulfur plus 4 times -2 is equal to 0. So we're going to have 2 plus S minus 8 is equal to 0, which is S minus 6 is equal to 0. So therefore S is equal to +6. Let's look at phosphate now. Let's do another example. If you remember, the phosphate anion has a -3 charge, so therefore it has to have a -3 oxidation number overall. So we have P plus 4 times oxygen, which once again I'm just going to call it OX, has to equal -3. Each oxygen has an oxidation number of -2. So we have P minus 8 is equal to -3. So the phosphorus has an oxidation number of +5. So why is this even useful, you may ask? Let's start to balance some simple oxidation equations. Okay, so here's an example. We have chromium in its solid form plus nickel, that's a nickel cation, in aqueous form, going to make chromium 3+ aqueous plus nickel solid. So underneath each one of these, in a different color, I'm going to write the oxidation number for each one. The oxidation number, that's not a very good color to use. The oxidation number for the chromium is 0. For the chromium solid, and the nickel solid is also 0 because those are in their elemental forms. The oxidation number of the nickel as a reactant is +2, and the oxidation number of the chromium is +3. The first step in balancing the redox reactions is you have to do what are called half reactions. This is so important. You need to balance each half reaction. Okay? So, let's break this up into half reactions. First, let's look at chromium. Chromium solid is going to chromium 3+ aqueous. The state isn't so important here. So, in order for it to be 3+, is it being oxidized or reduced? it's being oxidized because it's losing 3 electrons, because your charges overall have to balance. The other half reaction is nickel 2 plus, and I'm not going to write the state because the state isn't so important here, the state of it being aqueous. And it's gaining 2 electrons in order to become nickel solid. We now have to balance, the second step for this is we've got to balance the number of electrons. So if you look, here we have on the product side 3 electrons and on the reactant side 2 electrons. They are not balanced. So what's the lowest common multiple of this is 6. So in order for us to get 6 electrons, we're going to have to multiply this half reaction by 2 and this half reaction by 3. So let's do that. Let me erase the top here so that way we can see what I'm talking about. When we multiply the chromium reaction by 2, this is what we're going to end up getting. We're going to get 2 chromiums making 2 chromium cations plus 6 electrons. When we multiply the nickel reaction by 3, we get 3 nickel cations, making 3 nickel solids, plus, whoops. And we also have on the reactant side 6 electrons. See, because we have these 2 times 3 is 6. So now we just have to combine the 2 equations. Let me erase the board here. All right. So I'm going to go back to this color. So when we combine these two, we have 2 chromium solids plus 3 nickel, 2 plus aqueous, plus 6 electrons, is going to make 2 chromium cations aqueous, plus 6 electrons, plus 3 nickel solids. Now, if you notice, because I'm not skipping any steps, we have 6 electrons on the reactant side, 6 electrons on the product side. So those are balanced, and we can just cancel them out. And let's write our final balanced equation. This is 2 chromium solid plus 3 nickel cation in the aqueous state is going to make 2 chromiums in the aqueous state plus 3 nickels in the solid state. All right. Hopefully that has helped explain how to balance these equations. And now on your own, you should do some of the suggested problems at the back of the book. You can work through other additional examples, and in class we will try to do further discussions in our next lecture on how to do and balance these equations. Hopefully this has helped explain what oxidation reduction is and how to balance simple redox equations.